We'll cut the recording to right now.
Okay, all right. Pay no attention to those terrible things I was saying. Um, okay, here we are. I do that a lot. I don't know how. Anyway, so they kind of have a two-part puzzle. So they give you part one here, and then once you get that answer right, then you get down to part two, and they add some more constraints on what is this actually doing. It's like how much fuel each module needs. So that gives you a pretty simple algorithm to follow through. If I
Yeah, so
recall.
basically we're dividing something and then we're rounding down and then we're subtracting. And for the first problem, it's just a simple formula that gets applied once, right? But then the second one, you have some freedom in how you can implement that because you can either, this goes back to what we were doing with the binary search progression, where we were initially doing recursive algorithms to figure out how that works in Go. And recursion's a universal thing in other languages. So you can do a recursive approach or you can do an iterative approach. So what did you do in Rust? Did you do iterative or did you do
Iterative,
recursive?
yeah. I don't believe in recursion. It's evil. Um, yeah, so maybe the only interesting thing here is that I don't know how it works in Go, but in Rust you have kind of like default math, and then you can say you want to have saturating math. So in this case, I'm saying if this goes below zero on this unsigned U64, then we just keep it at zero. So that way we don't have any wraparound or anything like that. So you can just say, okay, well, I know when it saturates to zero that I can continue.
I haven't heard of that before. Saturated math.
Yeah. So it's really useful for when you might overflow. It's more expensive than because you have to do a check, right? But
Mm-hmm.
that way you don't overflow. You just get to the maximum or minimum number of your range and stay there.
Mm-hmm. That makes sense. Okay. Yeah, I haven't heard that term used before, but yeah, that makes sense with overflow and that. Cool. So where's your iterative approach?
So here saying, so I read the input file into a string, and then I take each line. So this is line method, and then I'm filter mapping, which means I am parsing it. If that is okay, then I turn it into a vector of U64. So I'm taking all those, each line, which let me show you what the input line looks like. Uh, so anyway, it's just a bunch of lines. So I'm just taking each of those, parsing them, validating that they do actually read as a U64, and if they don't read as U64, I just discard the line. So I just take the valid input. And then, so then here we iterate through. This copy just means that, well, anyway, it's complicated. Don't worry about that. And then we're just applying this function to each item within it. And then we're taking the sum of all of those to get the naive sum. And then here we're doing the same thing. And we're just applying this total fuel needed function to each item. That's really kind of
This is
confusing.
also part two then, because you're doing total
Yeah, this is
fuel
both part
versus
two.
fuel needed.
Yeah.
Okay.
I don't know
Oh,
if
I
I
see.
saved part
Naive
one.
sum and fuel sum.
Right.
Okay. Yeah, that's nice that you have like this mapping ability because in Go doesn't give you anything. you gotta you gotta build it from scratch. And when I approached the problem, I was thinking, oh, I'll create a little parser to like go through the string and split it by new line and whatever. But then I decided, I'll just do a little cheat in Vim and just, paste it and then just add a comma to it so that it's just one big array. Um,
Nice.
yeah, because when I first started the first problem, I didn't know if there was going to be like performance penalties. Like if I do a naive solution, am I going to be able to complete the problem? Because sometimes if someone's really crafty with these problems, they'll design something in such a way that the input data is so big that if you're not efficient enough, you'll like crash because if you do recursion and there's like too many, if you're doing too many stacks, if your recursion is going too many levels deep, then you might just your program might crash because you run out of space, right?
Yeah, so this solution to do both of them takes 130 milliseconds.
Yeah, it's like basically free. Yeah, so far I haven't seen that yet, but I've only done the first two and I'm on number 3.
Oh,
So
why don't you show us actual Go code since that's what we're here, Paul?
sure, we can go back and forth. We can do Go and then Rust and share that way. Let me see here. Where's my terminal? Got all this demo stuff left out from the Git demo. Okay.
Hi, Cindy.
How's it going, Cindy?
How's it going? I just wanted to see everybody else's solutions.
Yeah, she doesn't
I'm
talk to me
really
now that she's cool.
whatever.
Have you
Don't
been
talk to me.
doing? Are you on a certain day, Cindy?
I just started like a couple days ago, so I think I'm on day 3 still.
Okay, that's the same as me.
Yeah, day 3 is a little tricky, I think.
Yeah, I was looking at that and it reminds me of another problem I've seen before, but I don't quite know yet if the solution is the same. Like I'm just doing naive brute force solutions, just so I can work my way through it. And
Yeah.
then if I have time, I'll go back and say, oh, can I optimize this? But so far I haven't seen the need to do that with the way the problems are set up.
Oh, well, by the way, actually, my first one was time was wrong. That was including the time for like the Rust package manager. If you just run the binary bear, it's 7 milliseconds.
Hopefully everyone can see this okay. Got a 4K screen, so it can get bad on eyes over remote. So for day 1, pretty simple, but I don't have that parsing code. So let me pull up my test setup. That's where I like hide all the complexities here. So my approach was 2 things. Like first have a unit test to use the sample data they provide, because they have like in this case they have 4 small sets of data where they tell you exactly what you expect to get as an output. Oh, whoops, this is the wrong one. Why did I open? Is this the right one? No, this is the program one. I opened day 2. That's why. So they provided a number of example data points and what you expect the result to be. So I created a test just for that to make sure that everything was working correctly. And then I created a separate test to actually create the result for my custom data. So my custom data, like I was telling you guys, telling everyone that the modules are here in this list. I just copy and pasted it, and then in Vim, I just replaced all the end of lines with commas. So yeah, that's how I did it. So I had to avoid doing a parser. But for the other problems, I did write a parser, just because they were more complex, like the computer code problem. It has like a letter and a number, and then that's all separated by commas on a single line. This problem, they gave it to you on new lines, so I just copied and pasted it and then did a little replace job. So yeah, the only reason that I like this better is because, well, I mean, besides writing less code, it's a little faster because you don't have to parse it, but this is a really simple parsing job. Like it's a what do you call it? Premature optimization. So the solution you can see is pretty simple. Like I just rely on the fact that it's going to truncate the result anyway, because we're changing it to an integer here. So you don't need to use any kind of special library. The point you brought up about overflow, that's always a problem in Go. I don't typically deal with it very much, so I'm not really sure the best practice in Go for that. I do know that they have like special constants defined for like the max for every integer type. So if you do have an overflow, you can check if it's equal to that value. Actually, let me see if I can pull that up. If I can remember what the is it the math library? Yeah, so you see this right here, max int 8. It figures out what that value is. And so I think you can figure out overflow that way. But I'm not absolutely sure because I don't do a lot of math these days in my day-to-day code. So the recursive one, oh, and so basically, if we get a negative value, then we just return 0 by default, and that takes care of cases where the fuel is, you know, it's I think 3 or less. It would end up being a negative value. Yeah, 3 or less. So the recursive way, in order to do recursion, you have to have a base case, right? So the base case is this right here. Anytime that fuel is not greater than 0, we're just going to return fuel. Otherwise, if fuel is a positive number, then we're going to recurse. So it looks really elegant, but you have to, like, every time you do something recursive like this, I want to have a test so I can make sure that it's working properly, because there's like so many things can go wrong if you just don't place the right order of things. Recursion can totally, you know, bite you in the rear. So yeah, I wanted to rely on tests to tell me if I was doing it correctly. So I have a recursive version of the same thing down here with the data points that they provide.
I have a dumb question.
Go for it.
Why did you use floats?
So initially I thought we were going to have some floating point numbers. And so I just started that way. And it turns out that everything was an integer and I just kept it. But I don't think it needs to be a float because, well, so everything inside of here is going to be a float, right? Because you have a float divided by I think what Go does is it infers, since that you're dividing by a floating type, that the constant should also be a floating type. So this is a float divided by a float, and then you're going to cast that to an int. But it actually doesn't matter because if you look at the recursive solution on subsequent, the first time it runs, you provide a float and it calculates the fuel. And then on subsequent runs, you're taking an int and casting it to a float. So you lack precision. There's no floating values there, so you could have just put an int in there. So I think we're fine, but I might be wrong on that. So I'd have to do a little research and get back to you on if we need to have a float. But yeah, I think, well, we could do a little experiment right here. We can change this to an int.
I did mine with ints and just did the division and it just rounded down. So I didn't have that problem. Like,
okay.
Yeah.
That makes sense. Yeah. I would expect it to not have a problem. Just so we have some fun with the demo gods, I'll try it and see what happens. I have to change it everywhere else. All right, well, we'll leave that for another day. But yeah, Cindy, do you have your solution hosted anywhere? Do you want to share it?
I don't have it hosted anywhere, but mine is, I'm a little ashamed of it. So like, I can share it though.
Is there anything that you specifically you wanted to improve?
I wanted to write tests for it and I didn't get a chance because I just haven't really been prioritizing it. But I love how you did the test for this and you like randomized the input.
Oh, the inputs, I don't think the input's randomized. Yeah, the input is not randomized because so this is a slice of structs, so it's ordered. So it'll always run in the same order. It's always going to run these in the order they appear. If this were a map, then it would randomize the execution because the map traversal is random to a certain respect. But yeah, this will run exactly the same always. I don't know how they generate this data. It must be like a hash of your email or something that is used as a seed to generate all this data. I'm not really sure how they came up with this because it seems like I'm guessing they have a fairly stateless service and then they take your personal info and they They just use that to consistently create this data.
Yeah.
But yeah, if do you want to share day 1 or day 2, or does anyone else want to share?
I can share day 1.
Sure. Go for it.
This one. Yeah. So I just read the input in, and kind of went through the line, converted it, and so here I just did a total, like this function right here, which is where I did the integer. I didn't get a chance to do the testing, so I just kind of like tested it this way. Yeah.
If you like testing this way, one thing that you can do instead of like writing a main is that you can do an example test. Have you ever seen those?
I haven't seen those.
So an example test is a test that runs, but you don't have, in regular tests, they have testing.t, right? Where you can access the test framework. In an example test, you don't have access to that. You just have a function body, and what you do is you print to standard out. And then you use comments, just like how you have stuff commented out, you would actually put comments that say output : and then you would put what you expect to see on standard out. So if your example test runs as expected, it generates the output that the comments say, then it will pass. Otherwise, it'll fail. The nice thing about example tests is that if you use Godoc, you can actually see your examples in your documentation that gets generated by the Godoc web server. So if you have it hosted on a public repo, you can go to godoc.org and you can actually see your example tests. And I think you can run them too. I'm not sure about that part. But yeah, it's kind of similar to this style. It's like, oh, I want to print something to screen. I want to print something standard out, and I expect this value. And so it's a really handy way to write tests that like self-document. It's pretty cool.
Yeah, that sounds really cool. I'm gonna look into that.
Yeah, so I see one thing that you did differently from me is that you actually scanned everything as like a stream. You're using a scanner to go through the file and then pick it apart line by line so that the whole thing isn't loaded in memory. And that's pretty smart because the way I did it, I just hoped that it wasn't so big that it was going to become unwieldy. But I think it is kind of unwieldy because it like took up the entire source code file. But yeah, being able to parse it like that is another good way to do it. That's something that comes up a lot, is just making sure that you don't load everything in memory and ruin like server performance because all the memory's being hogged by a single request. So yeah, that's an important concept in Go. Cool. Do you have anything else you want to share?
No, I'll just this one.
Dimitri, do you have anything you want to share or any questions?
I have a quick question about the recursion function. Is it possible to apply some tail call optimization in Go?
You know, you're not the first person to ask that, and I forgot to look it up. I don't know the answer to that. Yeah, I have no idea. I'll have to look that up and get back to you. This is the second time this has come up. Yeah,
I haven't done anything in Go yet, but I did similar challenges in Scala and Ruby.
Go doesn't give you a lot of power over how the runtime operates. So if tail recursion optimization, if that's something that requires the runtime to behave differently, then I highly doubt that's in there. I mean, not even as a compile option. Yeah, I don't know how Go actually implements its recursion, so I'll have to look into that and get back to you. It's just kind of a black box to me.
Thanks.
Yeah, no problem. Have you been doing the advent of code?
Not yet.
Okay.
But I plan to.
I'm getting caught up because I started yesterday, so trying to power through and catch up to everyone in the Slack channel. So there's a Slack channel, Advent of Code, that a bunch of people are having discussions about the problems. So if you want to participate, that's available. Okay, cool. Let's see here. I can share the next day. Let me go back to my screen. My giant old man font screen. Everyone see that okay? So for day 2, let me pull up the what's going on here. Actually, I'll use this screen. So on day 2, the problem turns into this kind of interesting build a virtual computer type problem. And it's really neat because you learn a little bit about how programs are structured in memory, how they're fed in, and then you have this instruction pointer that's going from memory position to memory position, hopping around. So it's kind of like learning assembly to a certain extent. It's kind of abstracted and simplified a lot more than I remember from taking an assembly course, but it's the same general stuff. So this is a really cool problem that they provide. So just to go over what they're expecting here, they provide you a small program. And so, for example, let's say this program is only, I think this is 5 bytes right here. You read the first byte to figure out what operation it is, and then the next 3 bytes are your parameters for that operation. And then once you're done with that, you go to the next byte. So +4 from where you started, 1, 2, 3, 4. And then you read that code and you decide what to do next. So if it's 99, that means the program's done. Halt, you're done. If it's 1, that means add these to the values referenced by this address, and then store the result in the location referenced by this address. So now we've got pointers and we're dereferencing them to figure out where to put the value, or referencing to find out where it should be stored. So this is a pretty cool problem. It's teaching you a lot of things. Like it's possible to do this problem and not realize how much you learned because there's like so many hidden little pieces. So I really like this. This is really cool. So also, like the other problems, they give you some sample data and they tell you, they step through it. They say, here's the program, here's how it looks after the first operation runs, here's what it looks like after the last operation runs. So you've got one program there to plug into your tests. And then they give you a bunch of little baby programs and what you expect the program to look like at the end. So we've got, it looks like 5 sets of data to help us figure out if our computer is working properly before we start to run the main program. And this is something that I like to do first because I know that these little baby data sets are much easier to debug than if I were to run the full random set of input that they give me. That I do not want to debug because it's just, there's so many things that can go wrong in a large data set like that. I want to keep the data sets as small as possible, work out the kinks, and then move on to something more complex. So I'll share with you the Go version, and then I'm really curious to see the Rust version after this, Will, if you don't mind sharing.
Sure.
So this time I actually did write a parser. So this parser is very naive. So like Cindy, I was telling you, like I wasn't going to get too concerned about streaming it line by line or byte by byte. I just did the naive thing, which is load it into memory and split it. So I did a string split. I took the raw string, and the raw string is down, oh, it's in my test code. So you can see the raw string is Where is it? Must parse codes. Did I even use this? Maybe I didn't even use it. Actually, you know what? I abandoned this. But you could do it this way. You just split it on the comma, and then you just parse for integers. And I just, since this is a simple program, I just panic if it can't parse an int, because that means the input is wrong and we're guaranteed to have good input. So the program will just panic. So one thing I did that was a little fancy and I probably didn't need to do is I created an enum type. So I created a custom type of opcode, and then I assigned opcode the various values. So add is opcode 1, multiplies 2, halt is 99. You don't really need to do this if you're only going to reference it in one place. And that's what I found out as I ran through the program, is that it was overkill because I only needed to reference the codes in this, this function execute op. So execute op, what it does is it takes the input, the instruction pointer, which I just call I, and then all of the codes in the program. So all it does is it takes whatever's at I, and then it does a switch statement. Is it a add, multiply, or halt? So you can see from this code that I could have just put 1 here. Like I didn't need to do all this fancy casting to a type and all that. It's just overkill, and it kind of makes it harder to read. So in retrospect, I would have made this simpler. So if it's adding, what we're going to do is we're going to dereference the values at the +1 position and then the +2 position. So like we were talking about earlier, if you look over here on the left, that's the instruction pointer. This is the first parameter that needs to be dereferenced, and then the second value that needs to be dereferenced. So in this case, 0 refers to this position in the program. 0 again refers to this position. And then we want to store that at 1. So basically it's saying 1 + 1, store it here. So you're going to see it become 2. So that's what happens in the case of addition. Then if it's a multiplication problem or a instruction, so you can see here we have a multiplication problem because the first code is 2. And so we're taking this, whatever's dereferenced by here, position 3. So we're starting at 0. 0, 1, 2, 3. So 3 times the data at position 0. The data at position 0 is 2. So 3 times 2, and then store that at position 3. So 6. 2 times 3 is 6, stored at position 3. And then halt the program. So that's multiplication. So this is a pretty simple problem. Well, it's simple if you have the test set up and you know that you need to dereference everything. Like the dereferencing part is a little, I think a little bit of the tricky part of the problem is you have to realize that you're not executing the values there, but you're executing what's pointed to by those values. We're dealing with pointers here. So yeah, and then just in case we get some bad data, we're going to panic and say, I don't know what you're talking about. This operation code isn't valid. And that never happened because they didn't throw any curveballs like that. It's all valid data. So the last thing is really important. So we're going to execute this operation, and then we need to return a value that says keep proceeding with the program or stop. So what I did was I return a negative value if we're going to stop. Otherwise, I return the next place the instruction pointer should go. So normally it's going to be you add 4 because you're skipping ahead those 3 parameters. But in the case of halt, we're going to return -1. And then that makes our program loop pretty simple. So if you look at the bottom here, we just have a for loop, and our instruction pointer starts at position 0. And we're executing codes. And if that instruction pointer is less than 0, we just know the program is done. We've reached a halt code. Otherwise, we just keep going forever. So even if they give us bad data where the program is like going to keep going forever, the way I designed it, it'll stop when I think it'll panic with improper, it'll have an out of bounds error the way I wrote it. So if you forget to put a halt operation code in there, it'll eventually panic and say you tried to access something that does not exist. But the data that they gave us is all valid, so that never happened. So if you wanted to have a safe program that doesn't panic, you would need to check if the returned pointer here on line 55, if the next instruction pointer, if that is not within the bounds of the code slice, then that means you need to return some kind of error to the user so it doesn't panic. I didn't do that though, because I just trusted them. I knew they weren't going to give any curveballs. So another thing, this goes back to streaming again, is I load the entire program into memory and just run it. So if this was a huge program, this would, use a ton of memory. So a better solution might be to read it byte by byte, or if I read that I have a add byte or a multiply byte, then I only read the next 3 values or next 4 values and do that. So I only have like a total of 5 bytes in memory at any point in time, because someone could give you a gigabyte large program theoretically, and you would just load that in memory and waste all of your RAM or your swap space or whatever. So yeah, if you wanted to optimize this for real world use, you would want to have the ability to stream the input from a file or wherever it's coming from. So the most complex part of this is the test. Just because one thing I wanted to do with this test is I didn't want to use a testing framework to compare the values. So one of the weird things in Go is that you cannot compare slices because slices are, they dereference different values that can change. Or sorry, they reference different values that can change. And so because of that mutable aspect of them, they don't allow you to compare them. So you can't say, does this program equal this program? It's not gonna work. You need a helper function to do that. But one thing it does let you do is you can compare strings. So if you have a slice of bytes, you know that that slice of bytes is directly translates into a string. So you can just convert it to a string. And I don't think the Go runtime gives you a penalty when you convert a byte slice to a string. And then you can compare them that way. In this case, we have a slice of ints. So since they're ints, we can't convert them directly to a string. But what we can do is we can use the FUMPT or format library to create a string representation of that slice. So what I did is I created a string representation of the what I actually got from my program, and then what I expected, and I just compared the 2 strings. So this allows you to get around using a test framework like Testify or Ginkgo Gomega or whatever's out there. There's a ton of them. And another thing you can do is you can use a reflect, the reflect library that's part of this the standard lib, and you can use that to do like a deep equals and say, does this slice equal that slice? But this is nice because once you have a string representation, you can just print it too. So you only have to render that string once. So you can see here in my log messages, I say, oh, if I didn't get what I expected, I'm going to print that output to screen. So for example, if I change this, right, and then I run go test, run test execute program. Whoops, I spelt it wrong. Execute. So you can see that fail. When it fails, it gives me all this input, it gives me all this log output. It tells me the input, says what I got, what I wanted, and then I can easily see, oh, these 2 values right here are incorrect. So yeah, that's that's why I did this. This is a very nice thing to have, and it's used a lot in the Go community, and it's used so much that in the most recent version of Go in 1.13, they actually added the ability to deterministically print a map, and they wanted that specifically for tests. So, and not just for tests, but also for when you're logging stuff, and sometimes the same exact value will be printed differently, and that'll throw you off. But in tests, that's really important if you're comparing strings. So if you had to print a map, the traversal of a map is random by definition in Go. That's to prevent you from relying on the order to do things. Like if you expected that if you put something into a map first, that you would traverse that first, that is depending on an implementation detail. So the creators of the language, they decided by definition a map will be traversed in some pseudo random way. So because of that, you cannot print deterministically. But now, if I use this fumpt.sprint function and I provide a map, it will deterministically print that map every time in Go 1.13. And the way it does that is it has to sort the keys and then traverse the keys in sorted order. So there's a penalty to doing that. So if you had a giant map, you have to take that into account when you print it as a string now. And if you don't want that feature, then you have to traverse it yourself so that you don't incur that penalty. So it's kind of an interesting thing, but they threw that in there so that it would be easy to do tests if you're dealing with map types. Did anybody have any questions about that? I was rambling for a while there. So another thing is that a gotcha about this problem is that we're modifying the program in place, because we're going back and we're changing the value at this address. We're changing the value at that address. So one thing we have to be careful about is we don't want to contaminate our test data. So the thing that I did is I created a copy of the test data. So this is the input. At the end of the test, I want to compare, or sorry, I guess you don't need to worry about contaminating, but that might be an issue in other situations. But I did it anyway. So if you wanted to create a fresh, clean copy of something, like let's say this same data was being used in multiple tests, like if you defined it outside of this test, then that would be an issue. Because we're at the end of the test, we're gonna dirty this data. We're gonna save values. We're gonna change the value here. We're gonna change the value here. You know, you can see there's some differences, right? So for the sake of keeping the tests clean, we make a fresh copy of that data each time. So we allocate a integer slice, the size of the input, and then we copy the input to the variable we're going to use for the test, and then we use that variable here. So that's important if you have test fixtures that are shared by tests. In this case, it's not, because each one of these are only used once, exactly once, but that's not always the case. So that's why this little function right here, you could have declared this as a package variable, right? I could have said var my program equals int, and then put the program here, right? But the problem with that is that if I ran 2 tests, it would be, what do you call it? If I ran more than 1 test, it would overwrite that variable. So I need to make a copy of it. So this function actually creates a copy every single time. It's going to return this literal each time. So that effectively creates the copy for us. So when we get to part 2 of the problem, so let me backtrack a little bit. In part 1, we run our program, and they tell us before you run your program, you need to fix it first by changing these 2 values. So we change those 2 values, and then we run the program. In part 2, they say, okay, we don't know what those 2 values are for your program that you need to fix. You need to figure that out. And it can be between, each value can be between 0 and 99 inclusive. So basically, I just have 2 for loops here that try every possible combination. And then when we find the magic number that they told us that we want, then tell us what those 2 magic patched values are. So it's very important that I have a fresh, clean copy of the program every time I run this, because if I contaminated the test fixture, then each attempt would be futile, right? Like it just wouldn't work because the data is wrong. So yeah, that's something important in testing, is just always make sure that you're not contaminating your test fixtures. If you're sharing data between tests, that sort of thing. And in this case, we're dealing with mutability here. A slice is mutable. We're changing values. So if we want a fresh copy, we have to explicitly make a copy. So yeah, I think that's enough rambling for right now. I'm going to take a sip of water. Do anybody have any questions about that? Okay, cool. Will, did you want to share your version? I'm curious to see that.
Yeah, sure. Trying to add someone to the spam list, and I've had so many people on there now from all the spam issues that it's taken. Right. Okay. All right. Share hopefully the right screen this time. Maybe. All right. That should be the right one. Yeah, so like you said, Paul, the mutability is a problem. So my solution here is just every time I call this calc command, which calculates the end result of the program, I just clone the vector, which is the same thing as making a slice and go. And then I'm passing in the 2 arguments that are being modified. So for the initial one, we need 12 and 2, and then we have to do the vectorial solution of passing in 0 to 99 until we get a value that equals what we expect. So in the actual code, so we here we dereference or we set 1 and 2 to be the start values, and then we just loop through all of it, stepping by 4, and then we set the first index to be the value of 1, second index for the value of 2, third index, and the target to be the value of 3, and then we just use this match statement, which is like a select in Go, essentially, and we just this 10.
So that match statement, is that exactly the same as a switch, or is there something special about it? Because I think I've heard this a bit, because this is like pattern matching where you can, or maybe you could describe it.
Yeah, sure. So you can do a lot of stuff with types in particular. So like if this was like an option of, let me just create. Equals 0, I think this is the syntax. Anyway, so you can do all kinds of crazy stuff like that. And you could use some, it'll just executes them sequentially. All right.
So it'll do all of the cases that apply to it. It doesn't just stop with the first one that matches.
No, it stops. So like here we're saying, let me this. Anyway, so here we're saying if, so like X here is an option. Let me type here. Spell. We're saying, okay, so X is an option. We're saying if it is some, there is a value within it, and that something inside it is 0, then do stuff. Otherwise, if there's some, if it is some, but it's not that, so if it do not pass this test here, then do something else. And then this underscores the default case where we just do something or nothing or whatever. So that's the kind of stuff you can do with pattern matching.
Kind of like how the default case is just an underscore. I don't know why I like that, but
yeah, it's very sleek, I guess.
Yeah, I always wonder about that with programming languages, like when they use a lot of English words and how people in other countries who may not speak English, like they have to work with, unless they have like a localized version of the compiler, they have to work with the same keywords, right? So if you create something that's just punctuation based, it's a bit more localization friendly, I would think.
Yeah, I just saw something like a month or two ago about an Arabic language programming language. So it's like instead of being in English,
And
it's
that's also got to be left to right, right, for Arabic,
yeah, right to left, but yeah.
or right to left, yeah. Yeah, so there's all these interesting factors. I think in what is it in Japanese? It's not even
They
it's
can
like
do
up and
up to
down.
down. Yeah,
Yeah,
I
it's
think they can do
vertical.
left to right or up and down depending on how they feel that day.
Yeah. There's a cool editor for Mac. It's called I think it's Cot Editor is what it's called. It's a free open source editor, and it's developed by some Japanese developers, and they made it so that it's like optimized for doing the Japanese style of
Hmm.
the text traversing across the screen. But it works great for Western style also. Like it's a really cool slick editor. I wish it had more ability to like integrate plugins because it's really slick and
Cool.
really well designed.
What's
Did
that
you?
called? I want to
Uh,
look at.
I think it's COT editor, one word. Let me double check. It's a pretty minimalist GUI text editor. But it's open source, so you can contribute. I think you can write like little plugins, like very simple things. Um, but it's
Oh,
really
wow.
lean, very
Huh.
lean.
That's breaking my brain.
It's written entirely in Swift, so it's like got all the latest Apple, frameworks and all that. That's one thing they pride themselves on. Um, But yeah, if you just need a simple text editor to fire up once in a while, if you don't want to use Vim or whatever, it's something handy to have besides the default text editor on Mac. Cool. Well, did you write any tests, or did you just use like a main driver to get your
Yeah, I
results?
mean, we could do that right now.
So I'm not familiar with how tests are done in Rust. Is it similar to Go, where you have to provide like a special function name, or?
So actually, basically the way you do it is you just put this, let me bump up my text size. This is actually like visible to you. Sorry. There we go. Is that not going? Try that again. No, that's smaller. There we go. Okay.
Oh, we're in the desert. There we go. We lost your audio though. You're muted.
I think you're muted through Zoom.
Yeah. You
So
got
I
the
am.
little.
Thank you.
There you go.
All right. So we'll just do this real quick. And then we'll do, what is the expected output of this? Blah, blah, blah.
So that's a comment directive that pound test.
It is like a compiler directive. So it's saying, hey, treat this thing here as a test. So it's not going to be part of the main binary when you build your actual
So
thing.
everything that starts with pound is a compiler directive. It's not a comment that turns into a compiler directive.
Correct. It's actually going straight to the compiler. So like if I want to say I knew this was going to be the hot pass, so I could say inline here, and that'll make it that function. Stuff like that. It's these kinds of pound things are used a lot in Rust. So like if you want to say a given type has certain parameters that or traits, then you can just use pound derive. Anyway, it's complicated. Maybe
Yeah,
it's
you
not
miss that a
complicated.
lot in Go, because in Go you have to create like a whole new damn file in order to choose to compile one version or the other, stuff like that.
Okay. And I don't remember what the expected value of this is 3,500. Is that it? Okay.
Well, that seems pretty simple. That,
Yeah, let's see if it
you made
works.
it look easy at least.
Okay, yeah. Well, let's make it wrong so we can see what that looks like. Sorry about the dog.
Sounds like he's in trouble.
Yes. Yeah, okay. So here you can say, all right, so we expected to get 3,500. We got 3,501. Or actually, anyway, that's reversed, but yeah.
Mm-hmm.
So that's how you do tests in Rust. They're always in line in the same file, or like by convention, they're in line. They don't have to be. You could do it in a separate file entirely if you wanted to, but typically they're at the bottom.
Yeah, I don't know how I feel about that, like putting in the same file, because on one hand, it's very readable. You can see, oh, I expect this function to behave this way. On the other hand, if you have a lot of test code for, a small amount implementation code or the same amount of implementation code, then that file will get really big, really fast, right?
Yeah.
So, I mean, having a test there is like saying this is the contract that the code should follow. So that is kind of nice to have, not having to traverse between two files.
Yeah, if you had the truly huge test, then you might want to put it in another file, but I don't think I've actually seen that done.
Yeah. Cool. I think we're just about out of time. We're at the top of the hour here, so we should probably cut it loose so everyone can get back to work. Thanks for sharing, Will. Cindy, thanks for sharing. Dimitri, thank you for joining. I'm glad everyone got something out of today, the Advent. I think what we'll do next week is we'll just continue doing some more problems. If anyone wants to see a specific problem, just shout on the Slack channel, and I'll take a look at that and try to focus on that, because otherwise, if no one requests anything, I'm just going to keep moving on from day 3. We can just keep sharing in chronological order. But yeah, if you have solutions you want to share, if you have questions you want to ask, we can do that next week. And yeah, if you want to, I already mentioned the Slack channel. So the Slack channel has the link to the Advent of Code, which I think is just adventofcode2019.com or something.
Just adventofcode.com.
adventofcode.com. Okay. So yeah, if you want to participate, if you're watching this video, then check that out. And we'll be back next week. So thanks everyone. Appreciate it. Have a good day, and I'll upload this sometime this week.
Thanks, Paul.
Yeah, thanks.
Thank you.
Thank you. Bye.